So in the previous lecture, we started discussion on how TTT diagrams can be constructed. Now you can see, so this is a TTT curve, time temperature transformation curve for an eutectoid steel, which contains 0.8% carbon. Approximately, it contains 0.8% carbon. Now you can see it here. So in this TTT diagram, so this is a perlitic region. So this region is a perlitic region. So this is perlite plus bainitic region, and this is a fully martensite region, and this is a bainite. So we will try to understand this TTT diagram. You can see it here. So MS, nothing but martensitic start temperature. It is somewhere here. And this is M90 itself is nothing but martensite has completed transformation. So M90 we consider as martensitic 100% martensite, because 100% martensite it's very difficult to get it. So that we will discuss at the time of martensitic transformation. But just for time being, you understood that M90 itself is nothing but 100% martensite. And so this is a time axis, temperature axis. Now you are at 800 degrees centigrade, and suppose you can see, so this is the nose of a C curve. So this diagram we also call C curve. It looks like C, and this is the nose of a C curve. So when from, suppose you heat eutectoid steel at about 800 degrees centigrade and you cool it, you have some quenching mechanism available in that, an excellent quenching facility. And suppose you quench it with less than 1 second. So here, which phase do you get? Remember that 800 we have fully austenite, full homogeneous austenite. Somewhere here we have unstable austenite, still unstable austenite, still unstable austenite, still unstable austenite. But when you cross this martensitic start temperature, so this austenite will decompose into martensite. So that's why here we have martensite phase exists. So martensite is also called alpha prime. So martensite is a very hard and brittle phase. And obviously, so this cooling is not equilibrium cooling, it is a non-equilibrium cooling. So martensite is a non-equilibrium phase. So strictly speaking, all non-equilibrium phases has very high hardness compared to equilibrium phases. So non-equilibrium phases are generally preferred in heat treatment applications, in heat treaters. Okay, so this austenite transforms into martensite. So martensite itself is a separate phase. So martensite we call as alpha prime. So the structure or the crystal structure of this martensite is a body centered tetragonal, BCT. So ferrite crystal structure is BCC. So where A is equals to B is equals to C. But this is a body centered tetragonal. So A and B, they are not equals to C. So C is higher than the A and B. And during this austenite to martensitic transformation, so these you can see when you heat this sample at 0.8% carbon steel at more than 800, and when you quench it into the water, obviously you require water or any other brine solution in order to quench it to less than 1 second. So this is due to rapid cooling, so hardness of the sample gets increased. You can see some surface distortion exists over the sample. So after the quenching process, so steel becomes very hard. So that steel you cannot use as it is into the applications, because this is hardness of a steel. If you measure in Rockwell C scale, it goes to more than 40, more than 50 HRC. And such a high hardness samples we generally do not require in mechanical field. So we need to control the hardness of the steel sample. Now let us focus one more cycle now. So again, one more steel sample we will heat it at 800 degrees centigrade, and for less than 1 second we'll quench it somewhere here, less than 1 second, and hold it there. for prolonged time. You can see in between 300 to 400 degrees centigrade. I have not crossed the nose of the seeker. I have hold it there in between 300 to 400 degrees centigrade, and I am holding the sample in between 300 to 400 for prolonged time. Then I am pulling back. So which phase exists? So here in this particular scenario, you will get one more phase called bainite. So this bainite, again it is due to form due to the non-equilibrium cooling. So also this is a non-equilibrium phase. So bainite is a mixture of ferrite plus carbide. So bainite is a mixture of ferrite plus carbide. So here we have martensite, here we have bainite. Remember that for martensitic transformation, we have to cool it very fast, very rapidly. So there is no chance of diffusion of carbon atom. When diffusion starts, when you are allowing time for diffusion, but here you are not allowing time. Less than 1 second, you are quenching the samples into the brine solution or water. So means there is no time for diffusion. So all the carbon atoms are trapped. So due to this trapping of carbon atoms, hardness of the steel sample gets increased, distortion occurs, and that's why here you get supersaturated solid solution, because alpha austenite is a solid solution, alpha is also solid solution, but at this room temperature you should not have solid solution of in the eutectoid state, but you are quench it very rapidly, so you are not allowed time for diffusion of carbon atoms. So carbon atoms are present in austenite at octahedral sites, so they are trapped there itself. So they are trapped there itself. There is no time for diffuse out carbon atoms. If you allow time for diffusion, then carbon atoms can displace from their positions, but here you are not allowed time. So they are trapped in their sites, and that's why distortion occurs, and you will get supersaturated solid solution. So martensite is a supersaturated solid solution, and also it is a diffusion-less transformation. Without diffusion, martensite has transformed. So it's a diffusion-less. It is a hard and brittle phase. It's a non-equilibrium phase. It is a body-centered tetragonal phase, and it is a supersaturated solid solution. Okay, so these are the certain characteristics of the martensite. So coming back to bainite, it is a mixture of ferrite plus carbide. Remember that perlite, in the perlitic transformation we discussed, it is a combination of cementite plus ferrite. But bainite is a combination of ferrite plus carbide. So that we will discuss at the time of bainitic transformation. Now, from 800, suppose we'll go to one more color, black, maybe black. Okay. Somewhere here, in between 500 to 600, or let us say 600 degrees centigrade, somewhere here, and then hold it further. To which phase exists? Obviously perlite. Obviously perlite, and 100% perlite. Are you getting or not? So this TTT diagram, time temperature transformation curve, is very important. And by using this time temperature transformation curve, and based on the cooling rate, at least you can predict the final microstructure of the steels. Okay. So remember that we have perlite, then perlite plus bainite, then martensite. Okay. So it's very important. So this curve, let us erase all this. So this curve, cooling curve, which just touches the nose of the seeker, we call critical cooling rate. So this we call critical cooling rate, CCR. Okay, which just touches the nose of the seeker, we call critical cooling rate. Okay. So this is the complete TTT diagram for an eutectoid steel. You can see A is austenite, B is a bainite, P is a perlite, and N is a martensite. And this dash curve in between these nodes of is nothing but it is a 50% completion curve, 50% transformation completion curve. Now you can see it here below 200 degrees centigrade, so martensitic transformation starts. Okay. So as we discussed, below eutectoid temperature you should not have austenite, but still austenite exists. In real life situations, you do not have their, as far as phase diagram is concerned, we do not have austenite, but practically austenite exists, and that austenite is unstable austenite. So from A to B, when we hold the sample at B, we have unstable austenite there, and this unstable austenite transforms into perlite. You can see it here. Okay, so this is unstable austenite region. So unstable austenite means that has to be transformed into another phase. And above 727 degrees centigrade, we have stable austenite. So how perlite is forms from the austenite? We have already discussed that over these first cementite forms, then ferrite forms. So carbon plays very important role in perlitic transformation. So austenite precipitates Fe3C at eutectoid transformation. When slow cooled, this perlite looks like mother of pearl and it's called perlite. And this is a diffusion of carbon from perlite. So remember that again you get here coarse perlite and fine perlite. The reason behind formation of coarse perlite is slow cooling. When we go for fast cooling, you get fine perlite. Because why you will get fine perlite in fast cooling? Because there is no time for growth of cementite layers or ferritic region. Are you getting or not? There is no, you are not allowing so much of time for growth. So cooling rate is such a fast that diffusion of carbon fast starts very fastly, and you are not allowing to grow in size the cementite layers. So this cementite layers you are not allowing to grow it. So we will get fine cementite layers and fine ferritic region. So that's why you will get fine perlite. But suppose you are cooling it very slowly, then you are allowing sufficient time for diffusion of carbon atoms. Are you getting or not? You are allowing sufficient time of diffusion of carbon atom, and so that the cementite layers will grow in size. So this ferritic part region is also grows in size, and you will get coarse perlite. Remember that you are directly quenching into the water. There is no absolutely there is no time for available for diffusion. So you will not get perlite there. Suppose you are cooling in the air, then it is a moderately cooling, and you will get there fine perlite. Suppose you are cooling in the furnace itself, then it's a very slow cooling. In that case, you will get coarse perlite. So remember that for formation of perlite, the carbon is very important, and cooling rate is also important. So if you are going for air cooling or normalizing, we generally call normalizing mechanism. In that case, you will get fine perlite. But suppose you are cooling all the steel sample in the furnace itself, like annealing. In that case, you will get coarse perlite. This is the morphology of fine perlite and coarse perlite.